All right, let's do this. So before we get into it, just a quick heads up or a reminder. The lab this week is going to be project prep for the final project, Enemy AI. And I'm not sure, maybe this is something I should have announced a lot throughout the semester, but all the project prep labs are posted on the course website in case you weren't aware of that. For most of them, it's just saying, the outline of lab, which the TAs go through anyway, and a reminder to submit on Autolab. But this one, the primer lab has, at the bottom, hints for testing each of the 6 lecture tasks. So this can really help in your testing. Even outside of lab, you can still refer to this document and get those hints of how I expect you to test each one of these things. So if you're having trouble with any of the testing, make sure you refer to this doc. So I just wanted to point that out. Not much to say about it. So let's get into some content, Subtragos. Today we're going to start talking about binary trees and traversals and talking about our second data structure in this data structures learning objective. The third being graphs, which will be next week. So let's just learn about trees. So the lecture task for today admittedly doesn't have anything to do with trees, so this one's a little disconnected from the lecture content. You can do this with linked lists, but we're going to compute a path through a grid. So for the game, for the project 4, there's a 2D grid of XY locations. For a compute path, you're given 2 of these locations on the grid as their XY coordinates, and you need to compute a path from the first one, from the starting point to the ending point, with only moving in the 4 cardinal directions, up, down, left, right, so no diagonal movements, and return a valid shortest path between those 2 points. So if the points are 1, 3, and 2, 2, this would be a valid path. Move down 1 in the Y direction, and then up 1 in the X direction, and you'll be able to have that path, that shortest path from start to finish. For this one, you're just computing the simplest path from one of the simplest paths from point A to point B. Later on in the assignment, we're going to have these paths avoid walls, which will require graphs next week's content. For now, just give me a valid path from start to finish. And for your testing, keep in mind that you can have many valid paths. If your start point is like 1, 1 and your ending point is 10, 10, there are a lot of paths. You can go all the way to the right first and then up, or down rather. You can go over, then down, or you can take some zigzag diagonal-ish path, or go all over and then down some and then over. There are a lot and lots and lots of valid paths. So keep that in mind in testing, that your test needs to accept any valid path. It's a big hang-up that a lot of students have. They'll make sure their test case will say, did the method output this exact path? And, well, my correct solution probably isn't going to give the exact same path that your code did, even though they're both valid paths. And then the office hour question is, why am I failing a correct solution? So don't fall into that trap. Make sure your test code is accepting any valid path. So there's quite a bit of logic that has to go into the test cases to be able to test if a path is valid. And you can do that in 2 steps. Make sure it's of the shortest length. Make sure it starts at the start node, ends on the end node, and make sure every move on the path is valid. So there's quite a bit of checks to do in the testing. It's not just, did you return this exact path? Or if you're cute with your test cases, you can use test cases where there is only one possible solution. I don't even recall if you can get around all of my incorrect solutions like that, but you can try. All right. And for this lecture test, the big thing is, aside from just doing some logic, is returning a linked list. So you'll be creating your own linked list using the linked list node class. That's the big linked list part of the lecture task. All right, so let's talk about binary trees. So we're talking about, I guess, trees in general, but all the tree examples in this class will be binary trees, meaning that they'll have two child nodes. So a binary tree is very much like a linked list node, where a linked list node, and they'll both work off of node classes, A linked list node has a reference to the next node in the linked list, which has a reference to the next node of the linked list, which has a reference to the next node in the linked list, et cetera, until next is null, and that's the end of the linked list. For a binary tree, we're following that exact same structure with one change. Instead of a reference to the next node, we're going to have a reference to two nodes. And that's the only difference. That's the only difference between the structure of a linked list and the structure of a tree. That difference has a lot of implications, and the way we work with these two data structures will be significantly different because of that change. But that's the only change in the structure. And instead of next, we say the two nodes that are referred to by a node are the child nodes of that node, and those nodes have that node as a parent node. So there's a bit of vocab. This extends throughout like the whole family tree naming conventions. Like if a child of a child node is a grandchild node and grandparent node going in the reverse direction, there are aunt and uncle nodes. There's all kinds of terminology if you get deep into trees. Child and parent, these will be the two vocab words that I'll use throughout the lectures as we talk about trees. So instead of next, those are child nodes, two child nodes, instead of one next node like a linked list. And then if you refer back, that's referring to the parent node of that node. And visually, this is what a tree will look like. We can have a left, and we'll name them left and right, the child nodes. A left and right child node for each node, and the child nodes can be null, which indicates that that branch of the tree, there's all kinds of tree terminology too that we can use. That branch of the tree terminates when there's a null as the left or right child of a node. So this is a tree where the root node, and the root is like the head of a linked list. This is the node that kind of starts the whole tree. The root node has the value 5. Its left child has the value 2. Its right child has the value 8. Its left child's left child has the value -3, which has no children, and a right child of 4, which has no children, etc. This 8, the right child's left child, 7 with no children. Its right child, 14 with no children. So this is all the vocab that we can say. And we can say, like, this node here is the parent node to this node containing the value 14. So that's all the terminology of the structure of a tree. But fundamentally, nodes that have references to two other nodes instead of just one, difference between a tree and a linked list. Trees can be kind of lopsided like this. You don't always have to have a left and a right child. The left child can have a value, can have a reference to a node, while the right child has null, for example. This node has no left child, but does have a right child, and this node doesn't have any children at all. So we can have kind of, misshapen or lopsided trees like this. This is perfectly acceptable. And most importantly, our algorithms that we write for our trees have to be able to account for this. They have to be able to handle trees where they have one child, 0 children, 2 children. They have to account for all of those cases. I'm going to use this tree for the slides just because it's prettier on a slide. There's no other reason for that. Just because, it's nice and symmetrical, etc. So in the slides, I'll show this, but keep in mind that the trees you work with in your code don't always have to be this well structured where every node either has 2 or 0 children. I've seen that in a lot of office hours questions where the code is set up. If left and right are both null, then that's my base case. Else, hit the recursive step where I'm navigating to both children, and then they get all kinds of null pointer exceptions. Don't fall into that trap. A node can have one child. All right, so let's look at this in the code. The binary tree node class, this is it. It has its value, a reference to its left child, and a reference to its right child. And that's it. We're not going to add any methods to this. That's just what we're going to work with. That's what the binary tree node class is going to be. We're not going to add much inside of here. We're going to work with these references directly for the left and right child. And then any code that works with these trees, we're going to write that in our algorithms themselves, not in the binary tree node class. So this is the entire class for a binary tree node, and then everything else is how are we going to work with this thing? How are we going to work with these trees? When we have a reference to a binary tree node, which will represent the tree or the root of a tree, how are we going to work with that tree? So first, when we create a tree, there's no easy way to add elements to a tree. You can do it. We're not going to do it in 116. I'm going to save that one for CSE 250. So we're going to add by writing our references directly. I'm going to create a new root to the tree, and this creating the tree from the previous slide, where 5 is the root, has a left child of 2, a right child of 8, etc. We're going to create the root of the tree with the value 5 and null for its children, just some placeholder value. And then I'm going to overwrite those values. I'm going to say root.left equals a new node with the value 2. Root.right equals a new node with the value 8. Root.left.left equals a new node with the value -3, which is this node here. Root.left.left equals this new node. So I'm building this tree by manually setting the references to the nodes as I'm creating them. And this is going to build that tree from that previous slide. So for example, root.right.left equals this new node with 7. Root.right.left equals new node with the value 7 and left and right of null. So I did create the root node with null and null, but I've since set root.left equals a new node, root.right equals a new node, and overwrote those nulls with actual values. All right, so now that we have the structure of a tree, we can build a tree in our code and represent these as nodes that are scattered throughout heap space. How are we going to work with them? And specifically, I just want to answer one big question about these trees. How do we traverse them, which means how do we just visit every single node of a tree? With a linked list, this question was pretty easy. We're going to start at the first, maybe the details were a little tricky, but the theory behind it is easy. We're going to start with the first node, visit that one, then go to the next node, visit that one, go to the next node, visit that one, just like going down and visiting each element one at a time. But when we have a choice, now every time we visit a node, we can either go left or right. How are we going to visit every single node in a way that, one, we're actually visiting every node, we're not losing track of where we are? Like if we just go left, 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 how do we remember, if we visit this node, visit left, left is null, so we're done. How do we remember which ones we visited and which ones we haven't? So we're visiting every node exactly once. How are we keeping track of that? And how are we just navigating this tree in general? Like how do we decide when to go left or right in a consistent way? Which order do we want to visit these children in? So we're going to see 3 different orders: pre-order traversal, in-order traversal, and post-order traversal, which are going to give us 3 different orderings of visiting the nodes in a tree. So 3 different orders of visiting every node in a way that's going to make sure we visit every node exactly once. So to do that, we're going to write our traversal method, and specifically I want to call a function on the value of every single node. In my examples, I'm just going to use the print line function and just print all the values of each node. Of course, that's where we would do whatever you can code, whatever you want to do with every single value in the tree. You would put some function there where we can work with the data of that tree. So given a node that we're working on, that we're visiting, and a function that we want to call on every single value, we're going to do 3 different things. We're going to call the function on the node's value. So we get that one done. We visited this node. We're going to check that off our list of stuff to do. We're going to call the function on this node. Then we're going to make a recursive call of this method on the left child and make a recursive call on the right child. And that's it. And then recursion takes care of everything from there. Our base case is calling this on a node that is null. And our recursive step is saying, well, we're going to visit everything on the left subtree, everything on the right subtree, and visit this node itself. We call this a pre-order traversal because we're calling this function, or rather visiting this node's value before making the recursive calls, before visiting the left and right subtrees. So when we visit these nodes, and I'll go through one example when we do in order, I'm going to go through the whole example in detail. But for pre-order traversal, we're going to visit the node, so we're going to visit the root, make a recursive call on the left subtree, visit that value, make a recursive call on the left subtree, visit that value, base case, return, recursive call on the right value, base case, return, make a recursive call on the right value, left value, return, or base case, return, and then 14 finally is printed. So we're visiting the node and then making recursive calls to the child nodes. With a post-order traversal, we're going to do almost the same exact stuff, same exact thing, except we're going to call the function after both recursive calls. So now we're visiting the node after we visit both subtrees, after we go through all that recursion. So if we visit in this order, we're going to make recursive call, base case, then visit this node, return, recursive call, base case, visit 4, return, visit 2, return, recursive call, base case, visit, return, recursive call, base case, visit 14, return, visit 8, return, visit 5. So we get a completely different order that we're visiting these nodes in based on when we make the recursive call versus when we visit the node that we're considering, the current node that we're visiting. For in order, we're going to make that function call. We're going to visit the node that we're visiting right in between the two recursive calls. So we're going to visit the whole left subtree, visit this node, and then visit the entire right subtree through recursive calls. And this is the one I'll break down and explain it a bit slower, a bit more in detail. So an in-order traversal, we're going to start at the root. We're going to make a call with root as the node. And the function here is just going to be print line. We're just printing each element of this tree on a separate line. So we're going to get here. We're going to look at our code. Node is not null. We didn't hit our base case, so we're going to make a recursive call on the left node. So we make this call, make a recursive call on the left node. This call here, where node is root, is sitting right here on in-order traversal on the left node. And that frame is still on the stack. That frame is still on the stack waiting for this call to return so it can continue its execution and visit this node. So we haven't visited the node 5 yet, that value 5 yet. We're right here making this recursive call where on this node, on the left child with value 2 is going to make this recursive call. On its left child, this node containing negative 3. So we have 3 frames on the stack. These 2 frames both waiting for this method call to return, for that stack frame to return. Once that stack frame returns, they can continue execution. We're in this node, we're visiting this node where node is this node. Function is still print line, that's going to be the same throughout. And we're going to call in-order traversal on its left node, get another frame on the stack where execution is right here on a node that is null. So we made a call of in-order traversal of null and the function. Since node is null, this will be false. Our base case does nothing, and that stack frame is going to return. It's going to say, okay, node is null. I got nothing to do. I'm just going to return. So this stack frame returns. We're back in this stack frame, which just got its first method call returned. So it's going to continue its execution. It's going to call the function on its node and print -3. Finally get our first bit of action. We're going to print negative, did I hit up instead of down? We're going to print -3 to the screen. So we're calling print line on the node's value, which is -3 in this case. Get -3 to the screen, and then we're going to continue with this stack frame. The green box is always the active stack frame. Make its second recursive call on its right child. That's null, so there's nothing to do. So that returns. This stack frame got to the end of its method. So this stack frame gets to return, and we return execution back to this stack frame that was sitting there waiting for its in-order traversal of node.left to return. Now that that has returned, we're ready to continue execution, print 2 to the screen, and then make the second recursive call on its right node. On the right node, it's going to make a recursive call to its left node. That's null, returns, base case. Visit this node, print 4 to the screen. Second recursive call, null, base case, nothing to do. This method has ended, so this stack frame returns, and execution goes back to this node with 2. It just finished this line, so it's at the end of its method, and we're ready to return back to this initial call. We're finally all the way back up to the root node, and at this point, we've visited all of the nodes in the left subtree. So all its left child's children, grandchildren, etc. We went down that entire subtree. If there were more elements here, it would visit that entire subtree, everything on the left, before returning back up to 5. So that's happened. We printed -3, 2, and 4 to the screen. This whole subtree has been visited. So we return execution back to the initial call, print 5 to the screen, and then go visit that right subtree. So we're going to make this recursive call over to the right and do the same thing over on the right. Make the recursive call, makes a recursive call to its left child over here, which is going to make a recursive call to null. That's the base case, returns, print 7 to the screen, make another call with the base case of null, return. Visit 8. Make the recursive call to the right subtree, to base case, print, base case, return. We return back to 8, return back to 5, and finally we're at the end of the method for the original call. So we return execution back to the caller. Whoever called this initial top-level in-order traversal method, we're ready to give execution back to them. Stack frame returns, and we've printed everything to the screen. All right, let's sit on that for a little bit. Anybody have questions about this? About how trees work and how we're gonna traverse them? Those are the two big topics, by the way, of this week. What's the structure of a tree, and how do we traverse a tree? How do we just call a function on every element of the tree? And then the rest of this week is examples of that, applications of that. The next thing we're going to see is an application of how to represent an expression as a binary tree. And then Wednesday we'll talk about binary search trees, which will keep elements in a tree in sorted order, which this tree happens to be a binary search tree, not coincidentally. So this is the crux of it. If you understood everything in the past 25 minutes, you're pretty solid for your interview until the TA asks, what's an application of a binary tree? Then you'll be a little stuck. But But this will get you mostly through the interview questions for binary trees. And also the quiz. The quiz code is going to look very similar to the code that I gave you. You'll have some code like this. Most likely, I won't say 100%, but like 98%. The quiz will end up looking like this. Here's some code that creates a binary tree. Then we're going to call either pre-order, post-order, in-order traversal on it with some function. That might not be just print line. It might be a function that does some extra computation. So are there any questions on this before we go further? I don't want to go further and just have most of you just stuck on it. I'm going to be optimistic and say that everyone's just doing good with this. I've said this before, but I do think the content in this learning objective is easier to digest than the previous two learning objectives. It's easier to digest than OOP and FP, and especially concurrency. Concurrency comes and goes so fast, and it's pretty complex stuff. And once we get into this, it tones down. We are using OOP and FP in this. Like in this example right here, we created a new class. We're creating objects in the heap of type binary tree node. They have references to other objects on the heap, and we're passing a function into this method. So we can't talk about this before OOP and FP, but once we do have OOP and FP, I don't think this content's as difficult as what you've already survived, what you've already been through. So I'm going to take the silence as everybody's super duper good. Please let me know if I'm wrong. And I do have a challenge for you, for those of you, for the recursion doubters out there. If you're like, I don't need to know recursion, screw this recursion stuff, I'm using loops for life. My challenge to you is write at least one of these methods without recursion. Write these with a loop. It's possible, you can certainly do it. It is way more involved, way more difficult than writing them recursively. Recursively, these are nice, simple methods. Make 2 recursive calls and call a function. And that's it. And a check for your base case. That's it. Like, there's not a whole lot going on in the code here. The code is pretty expressive. Visit the left subtree, visit the node, visit the right subtree. With a loop, how do you write the structure of visit the subtree? It gets trickier. You'll have to do it if you are going to accept this challenge. If you want to go try this route, you're probably going to want a stack, or rather a list that you use as a stack, to remember which nodes you've visited and which child nodes of each node you've visited. You have a lot of bookkeeping to do to keep track of, have I visited the left child and or the right child of this node, and when am I calling the function? You have a lot of bookkeeping to do that. When we use recursion, all the bookkeeping is happening in the stack frames themselves. So we're taking advantage of the program stack to be able to keep track of what we've executed and what we haven't, what we've visited and what we haven't. All that's happening in stack frames by remembering where we are in the execution of this code, how far we've gotten. If you want to use a loop, you have to rebuild that, ideally with a stack that keeps track of what you've done. For each node, have I visited the left node? Have I visited this node? Have I visited the right node? Keep track of all that information yourself. It's doable. You can definitely do it. It's not absurdly hard, but your code will be more complex than this. So this is probably the first case where recursion really simplifies the problem. Pretty much anything we do with trees, recursion really, really helps out. It makes everything look a lot cleaner. So you're welcome to traverse trees without recursion, but good luck. I want to see that from you now. It'd be LT4, doing LT4 without recursion. It'd be nice to see. It'd be a nice little challenge. All right. Let's talk about expression trees. So let's talk about an application. I've introduced trees. We know the structure. We know how to visit each node in a tree. But why? Like, why care about trees? So expression trees are one answer, and then binary search trees on Wednesday will be another answer. So when your TA says, what's an application of binary trees? Like, why would we ever use this? Those are your choices, or if you do some research on your own. Expression trees helps us keep track of expressions, or binary search trees helping us store elements in sorted order with some nice efficient runtimes. So expression trees we're talking about today. We're going to represent an expression as a binary tree where each node is either an operator or an operand. If it's an operator, the operator will be evaluated on its children, on its left and right child. And if it's an operand, then it evaluates to itself. So if we have this expression from the previous lecture, from 2 lectures ago, and we want to represent it as an expression tree, each operator is going to be a node that operates on its left and right children. So this right here, this subtree, would be 12 minus 4. This can work recursively, so if an operator has a child that it itself is an operator, this operator will have to be evaluated first, which is how we're handling our order of operations. When an expression tree is like this, when an expression is represented as an expression tree, the order of operation is this has to be evaluated before we can do 8 plus division. This has to be evaluated before we can do minus addition. Like, that doesn't make sense. We have to evaluate the operators before evaluating anything. So if we want to evaluate this expression tree, we're going to take a subtree where an operator has 2 operands and evaluate that. Find the next expression that has 2 operands and no operators as the operands. Evaluate that. Evaluate this addition. Evaluate the subtraction. And we get down to a single node that has our value that we're looking for. Great, but why expression trees? So expression trees are a way to represent an expression that's neither infix nor postfix notation. So in the previous lecture where we talked about expressions, we had infix notation and we had postfix notation and said we can convert between these and we can represent an expression as either one of these. If we represent our expression as an expression tree, so in our code we have a tree structure that represents our expression, it is neither of those. But we can use that tree to build either expression, or even a prefix expression, which we didn't talk about. So I'm going to take this in-order traversal and modify it a little bit to visit each node in this tree. And the modification I'm making is adding these parentheses around each operator. If I'm visiting an operator, add parentheses. If I'm visiting an operand, just print that to the screen. This is going to give us a fully parenthesized expression, which means wherever we can fit parentheses, we're going to put them there. So even though order of operations would handle a lot of the order here, oh, this isn't even the same expression from the previous lecture. I don't have that multiplication in here. So we're going to add parentheses. Even though this 9 divided by 3 will be evaluated first, fully parenthesized means we're going to have parentheses there anyway. There's no ambiguity. That's going to be evaluated first just by following parentheses. Your PEMDAS turns into just P. Just evaluate the parentheses first, fully parenthesized, so you're never going to have an ambiguity there. Evaluate this, then this. Well, the 12 minus 4 probably first, and then the whole thing. So with an in-order traversal, we get our infix notation. And guess what? If we use a post-order traversal, we get our postfix notation. So if we travel in this, we don't even have to modify anything. We're just going to print the token, and then I'm going to separate them by spaces. So if we just do a post-order traversal on that expression tree, it will visit the nodes in the order of a postfix expression via magic. Challenge not accepted. If you can do it without recursion, you can do it without recursion. Nice. So if we visit this in post-order traversal, recursive call, base case, visit, return, visit, return, visit, return, recursion, visit, return, recursion, visit, return, recursion, visit, return, visit, return, visit, return, visit. So the post-order traversal is gives us the post-fix notation. And this is helpful for interpreters when like your expressions in your code, for example, are just basically strings. They're strings that need to be parsed by the interpreter. So the interpreter is going to, may or may not, depending on the interpreter, parse that expression, store it as an expression tree, and then do whatever it needs to do after that. If it needs to evaluate it, just evaluate it recursively. If it needs to represent it as a specific infix, postfix, prefix notation, it can do that. And just work with it however it wants to. Any questions? Ran out of slide. Are we supposed to end 2:40? I mean, we could just end a little early today. Yeah, let's just call it. All right. Good. Great lecture, everybody. Oh, question. One question. Hold on. Shrek 2? Oh, I don't know. I like Shrek 1. That's tough. Yeah, I gotta agree with that. Boo Shrek 2. I have to agree with Shrek 1. All right. See you everyone Wednesday.